All right, let's talk logic. Simple statements can be true or false, right? But what about something like x is greater than 3? Is that true? Is it false? Well, the answer is kind of weird. It's neither. And that little puzzle right there shows a huge crack in the foundation of basic logic. So today, we're going to explore the super powerful tools that fix this problem, predicates and quantifiers. Let's get into it. So let's just start right there with that question. Is the statement x is greater than 3 true, or is it false? Just take a second. What's your gut feeling?
If you were thinking, well, it depends, then you are exactly right. It's neither true nor false because we have no idea what x is. And that, as simple as it sounds, is a massive problem for the rules of basic logic. Let's dig into why.
Okay, so to really get why this is such a headache, we need to take a quick look at the absolute most basic building block of all logic. It's called the proposition. It's the foundation for everything, but as we're about to see, it has a critical weakness. A proposition is super simple. It's any statement that has to be either true or false. No middle ground. 2 plus 2 equals 4? Yep, that's true. Lahore is in China? Nope, that's false. But x is greater than 3? It doesn't fit. It's incomplete. It's just stuck in this weird logical limbo, waiting for more information. So, how do we fix this? How does logic get around this problem? Well, it introduces this fantastic new tool called a predicate. And the best way to think about it is like a fill-in-the-blank for logic. So a predicate is basically a proposition that's just waiting for a variable. It's a template. That statement, x is greater than 3, is a perfect example of a predicate. On its own, it's not true or false, but it is ready to become a true or false proposition the second we plug a value into that little x. And here's exactly how that works. Let's just call our predicate p of x to stand for the statement x greater than 3. Okay, so if we plug in 4 for x, our statement p of 4 becomes 4 greater than 3, which, yeah, that's true. But if we plug in 2 for x, our statement p of 2 becomes 2 greater than 3, and that's obviously false. See? By filling in the blank, we turn the template into a concrete statement that we can actually evaluate. Now, this structure is incredibly powerful because it lets us start breaking down regular everyday language. Take a sentence like, the car is red. We can split that into the subject, the car, which is our variable x, and the predicate, which is the property, is red. We can even handle multiple variables, like in Alice is friends with Bob. This is how we start to translate messy human language into the clean, unambiguous world of logic. Okay, great, so we've got these templates called predicates. But what if we don't want to talk about just one specific x? What if we want to make a bigger claim, like something is true for all things, or for at least one thing? For that, we need our next tool, quantifiers. And really, it all boils down to two main types. You've got the universal quantifier, that's the upside-down A symbol, which makes a statement about everything. And then you have the existential quantifier, the backwards E, which just makes a statement about at least one thing. These two little symbols are what give our predicates some serious power and scope. Let's start with the universal quantifier. When you use this guy, you are making a big, bold, sweeping claim about an entire group of things, what we call a domain. So for the domain of all real numbers, this statement says that for every single number x you can possibly think of, its square will be 0 or bigger. It's an absolute statement. No exceptions allowed. Now, the existential quantifier, on the other hand, is, well, it's way more chill. It's not trying to prove anything about everybody. It's just looking for one example. This statement here, it doesn't say all numbers are negative. It just says, hey, out there somewhere, there exists at least one number that is less than 0. All we have to do is find one, like, say, -5, and boom, the statement is true. Okay, so we can say all things are this way, and some things are this way. But what about saying not all things, or no things? This is where we get into negation. And it can be a little bit counterintuitive, but it's really cool once you get it. Here is the absolute golden rule. When you negate a quantifier, it flips to the other type, and the negation moves inside. So to say it's not true that all students have read the book, you don't say no students have read it. The true logical opposite is there exists at least one student who has not read the book. And likewise, to negate some student has read the book, you have to make the much stronger claim that for all students, it is true that they have not read it. This flip is everything. All right, we now have all of our pieces on the board. We've got propositions, we've got predicates, and we've got quantifiers. So now we can start putting them all together to translate some really complex, nuanced ideas into pure, rock-solid logic. But just like in math, where you had to learn PEMDAS, parentheses, exponents, all that stuff, logic has its own order of operations to make sure we all read a statement the same way. And as you can see, quantifiers are way up high on that list. They have a very high priority, which means you figure out what they apply to before you deal with things like and or, unless of course you use parentheses to change the order. This is absolutely crucial. And this is why that order matters so much. Take a look. These two English sentences seem really similar, right? But they mean completely different things. The first one says, one of two big things is true. Either every single student passed, or the teacher is absent. The second one is totally different. It makes a claim about each individual student. For any given student you pick, either that student passed or the teacher is absent. See how the placement of the quantifier, controlled by the parentheses, changes everything?
And it gets even more expressive when we start nesting quantifiers inside of each other. We can combine them to make these incredibly precise claims. Look at example 1. It says for any number you give me, I can find another number so that when you add them together, you get 0. That's literally the definition of an additive inverse. But look at example 2. That's claiming something wild, that there is one special person out there who knows everybody. The order really, really matters. Which brings us to this final comparison. Let's look at these two logical statements. They use the exact same ingredients, a for all quantifier, a there exists quantifier, and a predicate for loves. The only thing that's different is the order. The first one says, for every person X, there exists some person Y that X loves. The second one says, there exists some person Y such that for every person X, X loves Y. So I'll leave you with this final thought to chew on. Do these two statements actually mean the same thing? Think about it. One describes a world where everybody has someone to love. The other describes a world where there is one single person who is loved by everyone. By just swapping the order of our quantifiers, we change the meaning from a pretty common idea to something incredibly rare. That's the power and honestly the beauty of predicate logic.